Today, we're going to take a look at the trigonometric ratios. What I'm referring to is right triangle trigonometry. The way it works is we use one of the angles as a reference point. It's either going to be A or C, not the right angle. And we have names that describe ratios in every right triangle. There are 6 of them. We're only going to take a look at 3. The first one is sine. We shorten that to 3 letters. It's not sin, it's sine. And the sine of angle A is the opposite over the hypotenuse, or the length BC over AC. The second one is cosine. We shorten that to COS, cosine. The cosine of angle A is the adjacent over the hypotenuse, which would be AB. Looking at angle A, remember, the adjacent means next to. The side next to is AB. The next to side can never be the hypotenuse, ever. So it's the adjacent, AB, over the hypotenuse, AC. The adjacent can never be the hypotenuse. The last one is tangent. The tangent of angle A is opposite over adjacent. And opposite is BC, and adjacent is AB. Remember, the adjacent is the side next to the angle that is not the hypotenuse. The way we remember these 3 ratios is SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. SOHCAHTOA. Say that to yourself several times. The thing to keep in mind as you work with sine, cosine, and tangent is that all they are names that describe ratios in a right triangle that use an angle as a reference point. We could change our reference point. In the previous page, we used angle A, but we could certainly use angle C. What would that look like? If I use angle C and I talk about sine, my opposite is different. Sine, remember, is opposite over hypotenuse. Well, the opposite is right here. That would be AB over the hypotenuse is still the hypotenuse over AC. The cosine of angle C would equal the adjacent over the hypotenuse. And the adjacent is right here. That would be BC over AC. And the tangent of angle C is opposite over adjacent. Opposite over adjacent would be AB over BC. You heard me say that trigonometry is about ratios in right triangles, sine, cosine, and tangent. Ratios in right triangles or ratios in triangles might recall you back to something we did previously, and that was similarity. The reason right angle trigonometry works is that every triangle with those same angles has the same ratios for the sides. When I make a fraction and I go opposite over hypotenuse, if the triangle is a 20, 70, and a 90, when I make that fraction, it'll always make the same fraction because it has the same angles. It will be similar. Right angle trigonometry really works because every other triangle that I make with those same angles is similar. And that's what allows me to use it to find other lengths. What someone did many years ago is they built a table of values. They drew a whole bunch of triangles. They drew one that was a 1 degree, an 89, and a 90. Another that was 2, 88, and a 90. Another that was 3, 87, and a 90. Then a 4, an 86, and a 90. They built all these triangles, then they measured the sides, and they came up with those ratios. Here's a triangle that's a 70, 20, 90. I measured the sides. Those are the lengths I got. I could build trig ratios using this. I know what the sine of 20 degrees is. Sine SOHCAHTOA. Sine is opposite over hypotenuse. Opposite, it's 34 over hypotenuse. Opposite the right angle is a 99. Then we go to the calculator and we divide those, and this is approximate, so I'm just going to round to the 100th. 0.34, about. Then we could do the cosine of 20 degrees. Cosine is adjacent over hypotenuse. I'm looking at the 20-degree angle. I want the side that is adjacent, not the hypotenuse. The adjacent side, the one next to, is 92 over the hypotenuse is 99. And then I could divide that on the calculator, and I get about 0.93. And I could do tangent. The tangent of 20 degrees, tangent is SOHCAHTOA is opposite over adjacent. The tangent of 20, this is my point of reference, is opposite, that's 34, over adjacent. Side adjacent is not the hypotenuse ever. Hypotenuse is always just the hypotenuse. The side next to the 20 then is the 92. We get about 0.37. I use the 20 as my point of reference, but I could certainly use the 70 as my point of reference. Then if I did the sine of 70, I'm looking at the 70, sine is opposite over hypotenuse. The opposite side is the 92, and the hypotenuse opposite the right angle is the 99. Notice that we already did that right here. So this is about 0.93. The cosine of 70, 70 is our point of reference. Cosine is adjacent over hypotenuse. The adjacent side is never the hypotenuse. So the adjacent is the 34. Cosine is adjacent over hypotenuse. The hypotenuse is 99. And look, we already did that. It's 0.34. And then the tangent of 70, tangent is opposite over the side next to the adjacent. Opposite, tangent is opposite over adjacent. And that would be 92 over 34. Notice right here that these two are reciprocals of each other. 92 divided by 34 is 2.71. So this is about 2.71. What you need to observe here is that since 70 and 20 are in the same triangle, they are using the same side lengths, then you get those same numbers that repeat. The sine of 20 is the same as the cosine of 70, and the cosine of 20 is the sine of 70. And then notice that the tangent of 20 and the tangent of 70, those are reciprocals of each other. Remember what I said just a few minutes ago. I could take and draw triangles, a 1 degree, an 89, and a 90, a 2, an 88, and a 90, a 3, an 87, and a 90. And I could do all of those. I could do a 20, a 70, and a 90, a 21, a 69, and a 90. And I could measure the sides and build these ratios. And that's what someone did when they developed trigonometry. Here are all those ratios. Again, note that 20 degrees, these are more accurate than my crudely drawn one. That 0.3420 is right there, 0.3420. 0.93, this is the sine, this is the cosine, this is the tangent, and this is the sine, and this is the cosine, and this is the tangent, that row. And these two, the tangents, they're reciprocals of each other. If I put this over 1, 0.3640 over 1, and I flipped it, 1 divided by 0.3640, I get that number right there. And if you look at any pair that add to 90, they're in the same triangle. If I do 16 and 74 add to 90. They are ratios from the same triangle, a similar triangle at the very least. 0.2756, 0.2756. The sine and the cosine, that's the middle one on the right, they end up being the same value. Here's the cosine of 16 and the sine of 16. Those end up being the same value. And the tangent of 16, if I put this over 1 and I flip it, 1 divided by 0.2867, I get this value right here. These ratios all repeat in different locations as we build this table of trigonometric values. Your calculator has these values stored a lot more accurately, but what you need to do is make sure you're in degrees. There's another way to measure angles called radians. We are going to use degrees. If you go to the Desmos calculator online, you need to click the little tool icon and change it to degrees, or every problem you work out will be the wrong answer. My goal here was to give you an idea where trigonometry came from. Now let's see how you could use trigonometry to solve for sides in right triangles. In this triangle, we're trying to find x and y, and we're given that angle A is 50 degrees and the hypotenuse, the side opposite the right angle, is 20. Let's find x. First thing I want you to realize is that you can use either angle. I could use the 50 degrees as my point of reference, but if I wanted, I could find angle C and use it as my point of reference. I know that the top angle here is 90 degrees, and there's only 90 left to make 180, and 90 minus 50 is 40 degrees. Angle C is 40 degrees, and I could use that as my point of reference too. Either one works fine. I'm going to stick with the 50 degrees. This is my point of reference. And I'm going to find x. X is adjacent. It's next to the angle. Reminder, the hypotenuse is never the adjacent. So we're dealing with adjacent and hypotenuse. And that brings us back to SOHCAHTOA. Adjacent and a hypotenuse. Cosine is adjacent over hypotenuse. The cosine of 50 degrees is equal to the adjacent x over the hypotenuse, which is 20. The cosine of 50, it's a decimal. We treat it like any other number. We'll put it over 1 and we'll cross multiply. X times 1 is x. 20 times cosine 50 is 20 cosine 50. Before we put this in the calculator, we need to make sure we're in degrees, not radians. Desmos always defaults to radians. If you go to the page and change the settings, it'll stay that way until you close it. But you need to go to the tool, it's in the upper right, and go down and click on degrees. If you don't do this, every answer you get is going to be wrong. 20 times the cosine of 50 is about, we'll round to the 10th, about 12.9. Now let's find y. I'm using 50 as my point of reference. Y is the opposite. And the number I have is 20, which is the hypotenuse. Opposite and hypotenuse, that's right there. That would be sine. So katoa. The sine of 50 degrees equals the opposite, y, over the hypotenuse, 20. This is a decimal. I'm just going to put it over 1 and treat it like any other number. Y times 1 is y. 20 times the sine of 50. According to this, y would be, and by the way, I closed the page and opened the page, and again, Desmos went back to radians. You need to make sure you're in degrees or everything is wrong. Here we get about 15 to the 10th, 0.3. The last thing I want to point out here is I use the 50 degrees as my point of reference. I could have just as easily used the 40, but it would have worked out slightly different. If I'd wanted to find out x, x would have been the opposite, and 20 is the hypotenuse. It would have been opposite and hypotenuse, which is sine. I could have got that same answer for x if I'd used sine of 40, and then that would have been opposite over hypotenuse, x over 20, and I could have put that over 1 and cross multiplied, and x would have been 20 sine 40. Putting that in the calculator would have given me the same exact answer. I could have found y using that 40-degree angle too. Using the 40, y would have been the adjacent. Reminder, the adjacent is never the hypotenuse. Adjacent over hypotenuse, that would have been cosine, and the cosine of 40 would be y over 20, and put that over 1 and cross multiply. Y would have been 20 times the cosine of 40. This would have given you the same exact answer for y as that original equation. Make sure you watch this example carefully because this will end up a little bit different than the previous example. Let's find x and y here. If I want to find x, I can see that 42 is the opposite, x is the adjacent, because the hypotenuse is always the hypotenuse. I'm going to go back to SOHCAHTOA, and if I want to find x, the number I have is the opposite, 42, if 55 is my point of reference, and the adjacent x. Opposite and adjacent. Opposite and adjacent is right there. That would be tangent. So I'll write the tangent of 55 degrees equals the opposite, which is 42, over the adjacent x. The solving ends up being a little different here because x is in the denominator. We need to divide to solve. I'll cross multiply. 42 times 1 is 42. X times the tangent of 55 is x times the tangent of 55. Remember your inverse operation. To get x by itself, I need to eliminate this multiplication, which means I need to divide. Tangent of 55 is just a number. It's a decimal. I'm going to divide both sides by that number. The tangent of 55, the tangent of 55, and I'll put this in the calculator. It looks like x is about 29.4 to the 10th. Now let's find y. If I want to find y, that's the hypotenuse. So I have the hypotenuse, and remember my point of reference is 55 degrees, and the opposite. So opposite, 42 is opposite to 55, and y is the hypotenuse. Opposite and hypotenuse. That is sine. The sine of 55 equals the opposite, 42, over the hypotenuse, x. Put this over 1 and cross multiply. 42 times 1 is 42, and x times the sine of 55. Get the x by itself. To get rid of that multiplication, we divide. Divide both sides by the sine of 55. Put this in the calculator. 42 divided by the sine of 55. That looks to be about 51.3 to the 10th. Just like I said in the previous example, if you had wanted, you could have just as easily used 35 as your point of reference. That would have worked just fine. Either angle. It can't be the right angle. It's got to be one of the acute angles. The last thing we need to talk about in the teaching part of the video is a quick review of the 30-60-90 triangle and the 45-45-90 triangle. Remember, the 30-60-90 triangle came from an equilateral triangle. All sides were equal here. What I'm going to do is drop a height. That splits that equilateral triangle into two congruent triangles. And a height or an altitude is always at a right angle. Those two triangles are congruent by hypotenuse leg. An equilateral triangle has all angles 60, which makes each of these 30. What they did was they called each side 2, which made each of these pieces 1. And then we used Pythagorean theorem to find the height. A squared plus b squared is c squared, where c is the hypotenuse. 1 squared plus h squared equals 2 squared. That's 1 plus h squared equals 4. H squared then equals, subtract 1 from each side, 3. And square root, we see that h is root 3. You might remember that we called the sides 2t, t, and t root 3 because every other triangle was similar to that triangle. It was some multiple of that triangle. But here in trigonometry, we're just going to use the sides 1, 2, and root 3. Notice that the 2 is the hypotenuse. Notice where they're going, between the 30 and the 60. Notice the short side between the 60 and the 90 is 1. And the altitude, the height between the 90 and the 30 is root 3. You've got to know where they go because you're going to be asked to find exact values for sine, cosine, and tangent of 30 and 60 degrees. The 45-45-90 triangle, special right triangle, came from a square. They called each side 1. Notice it's isosceles. And we know that it's a square, so we have a right angle in the corner. And these two triangles are congruent by side, side, side because they share a side. Since it's isosceles and we only have 180 degrees, we know that each of these are 45 degrees. The isosceles triangle has two equal sides and two equal angles. Using the Pythagorean theorem, we can again find that diagonal. Let's call that D for diagonal. A squared plus b squared is c squared, and c is the hypotenuse, opposite the right angle. 1 squared plus 1 squared equals d squared. 1 plus 1 equals d squared. 2 is d squared. Square root of both sides, and we see that d is the square root of 2. When we used these previously, we again used the idea that every 45-45-90 triangle is similar, it has the same shape, it's some multiple of that same triangle. And we call the sides 1t, 1t, and t root 2, or t, t, and t root 2. But in trigonometry, we're just going to use the lengths 1, 1, and root 2 to find exact values of sine, cosine, and tangent of 45 degrees. What you need to be able to do is see a isosceles right triangle and understand that it's a 45, 45, 90, and that the side lengths are 1, 1, and root 2. They're in that ratio. And when you see a 30, 60, 90, you need to be picturing in your head that it's always half of an equilateral triangle, if you can imagine that. Remember, the side lengths in that triangle were 2, 2, and the other one was 2, and we split it in half, and it was 1 and 1. And we found the altitude by using Pythagorean theorem between the 30 and the 90 was the root 3. You've got to be able to easily understand where those lengths go. The hypotenuse is 2. Between the 60 and 90, the short side is 1. Between the 30 and the 90 is the root 3. As I said, you'll be asked to find exact values of sine, cosine, tangent of these angles. Let's find the sine of 45 degrees. We remember SOHCAHTOA. The sine of 45 degrees is opposite over hypotenuse. Opposite, which is 1, over hypotenuse, which is root 2. Reminder, we don't normally leave a root in the denominator. If there's a root in the denominator, we rationalize the denominator. To do that, we take the root in the denominator and we multiply by root 2 over root 2. Whatever the root is in the denominator, make a 1 out of it, and then multiply straight across. 1 times root 2 is root 2. Root 2 times root 2 is root 4, but the square root of 4 is 2. The goal is to make a whole number or an integer in the denominator. So the sine of 45 as an exact value is root 2 over 2. Notice that if you go to your calculator, the sine of 45, you get 0.7071067812. We can't be exact. We have to approximate when we find sine, cosine, and tangent a lot of the time, majority of the time. But we can find the exact value of sine of 45. It's root 2 over 2. And if you put that in the calculator, you get 0.7071067812. The difference is this is exact, it's unrounded. We can find exact values for 45 degrees, 30, 60, for sine, cosine, and tangent. If I asked for the tangent of 30 degrees, tangent, TOA, is opposite over adjacent. The opposite is the 1. The adjacent next to, not the hypotenuse, is the root 3. We don't usually have a root in the denominator, so we're going to rationalize to make a 1 out of it and go straight across. 1 times root 3 is 1 root 3, or root 3. Root 3 times root 3 is the square root of 9, but the square root of 9 will be 3. And that is the exact value for the tangent of 30. You can check root 3 over 3 on your calculator and check the tangent of 30 on your calculator as decimals. You'll see they're exactly the same. If I asked you for the sine of 30 degrees, you get a real nice answer. Sine is opposite over hypotenuse. It's 1/2. And as long as your calculator is in degrees, when you punch in the sine of 30, you will see that it is 0.5 on the calculator. Same exact value. The rest of this video is questions from your assignment. Question 1. You know the measures of angle F, T, and N. T and N are side lengths. And we're going to decide which ratio to use. Well, this is the hypotenuse, and this is the adjacent. And we remember SOHCAHTOA, hypotenuse and adjacent. Go find that. Hey, there it is. It's cosine. Question 5. Consider this right triangle. Determine whether each equation is correct. So we go through each one. The sine of B, SOHCAHTOA. So we're looking at B as our point of reference. Sine is opposite over hypotenuse. Opposite, which is 11, over hypotenuse, which is 13. Hey, that looks good. Yes. Cosine of A. Our point of reference is A. Cosine is adjacent. Cosine is adjacent over hypotenuse. Adjacent next to is 11. Hypotenuse is 13. Uh-oh, they got the wrong one there. It's no. The tangent of B. Tangent of B. B is our point of reference. Tangent is opposite over adjacent. The opposite is 11. The adjacent is 7 because the hypotenuse is always the hypotenuse. It's never the adjacent. Opposite over adjacent is 11 over 7. Looks good. The last one, sine of A. A is our point of reference. Sine is opposite over hypotenuse. Opposite is 7. Hypotenuse is 13. 7 over 13. This one's wrong. Question 8. Let's label the side lengths correctly. This is a 30, 60, 90. It's half of an equilateral triangle. Picture what that triangle used to look like. It was a full equilateral triangle, and now we only have half. Remember, we have called each side 2, and each of these were 1, and the height of the equilateral triangle was √3, sometimes called an altitude. A is 1, B is 2, and C is √3. Question 14. We're going to find the exact value of the sine of 30 degrees. SOHCAHTOA. Sine is opposite over hypotenuse. Opposite over hypotenuse. It is 1 over 2. Keep in mind, if you were asked for the cosine of 30 degrees, as an example, it would be adjacent over hypotenuse, and adjacent would have been √3 over 2. If you'd been asked for the tangent of 30 degrees, tangent would have been TOA, opposite over adjacent. Opposite is the 1, the adjacent is the √3, and then we would have had to rationalize. √3 over √3, 1 times √3 is √3, √3 times √3 is the square root of 9, but the square root of 9 is 3. This is the answer for the sine of 30, though. Question 15. Back to your SOHCAHTOA. Cosine of 45. We're right there. Cosine is adjacent over hypotenuse. Here's the 45. The adjacent is 1, because the hypotenuse is always the hypotenuse, over √2. There's my hypotenuse. The cosine of 45 would be adjacent 1 over hypotenuse √2. We don't leave a root in the denominator. We make a 1 out of it, and we multiply straight across. 1 times √2 is 1 √2, or √2. √2 times √2 is the square root of 4. The square root of 4 is 2. √2 over 2 is the answer. Now we're going to find some lengths. And as we do each question, we need to remember SOHCAHTOA. Look at what we have. We have a 52. Remember, you could find that angle and use it if you wanted, but I'm just going to use the 52. We have the opposite side, x, opposite, and we have the hypotenuse. Opposite and hypotenuse is sine. The sine of 52 is equal to the opposite x over the hypotenuse, 150. We'll put this over 1, and we'll cross multiply. X times 1 is x. 150 times the sine of 52. Put this in the calculator. Make sure you're in degrees. The answer is 118.2. Question 20. SOHCAHTOA. We have the opposite side. We're using 40 as our point of reference. Opposite is x. And this is the adjacent side. Opposite and adjacent. That's tangent. The tangent of 40 is equal to opposite x over adjacent 143. We'll put that over 1 and cross multiply. X times 1 is x. 143 times the tan of 40. Put that in the calculator. Now this is interesting. I got 119.9912. Now we're going to round to the 10th. We look one digit over, that bumps this to a 10, and we have to carry it. So it looks like this is 120.0, which you can just say 120. Question 22. Our point of reference is the 57 degrees. X is the adjacent. 103 is the opposite. Adjacent and opposite is tangent again. The tangent of 57 is equal to the opposite, 103, over the adjacent, x. X is in the denominator, which means when we solve, we're going to have to divide. X times the tangent of 57 is equal to 1 times 103. Get the x by itself. We'll divide by the tangent of 57. It looks like x is about 66.9 to the 10th. Question 23. Our point of reference is 35 degrees. X is the hypotenuse. And 125 is the adjacent. That means next to. So adjacent and hypotenuse. Adjacent and hypotenuse. There it is. That's cosine. The cosine of 35 is equal to the adjacent, 125, over the hypotenuse, x. Notice x is in the denominator again. We'll put this over 1 and cross multiply. X times the cosine of 35 is equal to 1 times 125, which is 125. Get the x by itself, divide. I got 152.6. Number 18, let's find x here. Our point of reference is the 51. X is the adjacent. 90 is the opposite. Opposite and adjacent is tangent. The tangent of 51 is equal to 90 over x. Cross multiply. 90 equals x times the tangent of 51 and divide. We get about 72.9. And question 27. 32 degrees is our point of reference. 80 is the opposite. X is the hypotenuse. We have opposite and hypotenuse. That's sine. The sine of 32 is equal to the opposite, 80, over the hypotenuse, which is x. X is in the denominator. When we cross multiply, we're going to have to divide to solve. It'll be x times the sine of 32 is 1 times 80, which is 80. Get the x by itself, we divide by the sine of 32. And 80 divided by the sine of 32 is about 150.9663 and so on. We're rounding to the 10th, so we're going to use that number. That'll bump the 9 to a 10, and we carry it over. That means that x is 151.0.